sharing your valuable time with us. Let me take this honor of introducing Dr. A.G. Krishnakant Garu to you all. Dr. A.G. Krishnakant Garu is currently the Director of Analog Mixed Signal R&D Department at AMS Osram Group. He is an IEEE senior member and currently the Vice Chair of IEEE CAS EDS Hyderabad chapter and frequently delivers technical lectures at various universities. He received his PhD from IIT Hyderabad. He finished his BTech and MTech from IIT Bombay with specialization in microelectronics. He was awarded President of India Shankar Dayal Sharma Gold Medal and IIT Bombay Student Roll of Honor in 2002. Analog IC design is his passion and his specialization includes sensors and sensor interfaces, high performance analog signal processing, power management for automotive and consumer semiconductor IC design. He has 12 patents and 10 IEEE publications. He is one of the designated AE for TCAS2 for 24 and 25. We request the audience to join us in welcoming Dr. A.G. Krishnakant Garu, Director AMS Osram, to address the gathering.
Good afternoon, everyone. First of all, I'd like to thank the management of VNR Vignan Jyoti for inviting me to be part of this elite panel of members to share a few thoughts on semiconductor talent and vision. I would like to start from where Venkat Garu has left the discussion. Electronics engineering is not a 9-to-5 job. See, it's so maybe for the semiconductor, right? I don't have slides, so it's going to be maybe a short conversation, with some thoughts, and then maybe hopefully this will trigger some more discussion later on. So let's say we are think of a scenario where we want to manufacture 1 billion devices, which when designed today works well in the field for next 10, 15, 20, 25 years. Okay. So first point being manufacturing 1 billion devices. Why? The number of smartphones, the number of cars, the increasing number of electronics that are going into everyday application means we have to design more and more semiconductor chips. Okay. Now, as faculty members, you would have already encouraged your students to test some circuits in the lab. Electronics engineering and experimental field. You have to be hands-on. Go to the lab, test something, see something that is working. So unlike, of course, there's a lot of software, there's a lot of automation. We sit in front of the computer, we design things, but in the end, right, it's about seeing something real in the lab. So fundamentally, moving from a computer science background to an electrical engineering field essentially means that the students or the faculty members and the industries, everybody have to be willing to have the patience to be hands-on in the lab, sit in the lab, willing to solder, test it, you design for it, you look into the application, see what are the problems with it, the root cause analysis, so all of this. So the essential rigor of doing something with real components, real hardware, that's the beauty of the electrical engineering, electronics and semicon field. So going back to the theme, right? If you have to manufacture 1 billion devices, it's not only about manufacturing, but it's also about design and testing, right? Now I'll give you a simple scenario where you can now see how difficult the issue is going to be. Imagine we design a circuit, let's say a simple PLL or a simple filter or an op-amp based simple timer or a clock oscillator. If you encourage your student to sit and then design this in a PCB, right? Design this on a PCB, how much time would it take? Would you think it'll take the student to get the circuit running? Let's say you have a hardware piece. How much time? Take a guess. How much time does it take for a student to design, let's say, an amplifier? Take a piece of hardware, design an R1 by R2 circuit, simple amplifier. How much time does it take in the lab? Yes? Yes. 10 minutes. Great, ma'am. So assume that student is smart and is able to design and test something in 10 minutes. This means 6 in an hour and probably 140 in a day if you're working non-stop, and you do a multiplication in a month, 42,000, so on. Now, if you see, even in a year or even in 10 years, we'll not be able to generate even 1 million devices. Right? Simple math. Essentially means that the way we are designing or the way we are testing as per our academic curriculum is significantly different compared to the way it goes on finally into the production. So there needs to be a way to identify how we can speed up the testing, how we can do the application testing, the actual scenario where this piece of hardware is working, and then so on. And this whole 10 minutes what we are taking to test one simple circuit, imagine we scale it up. We want to test thousands of such functions, analog, digital, everything all processing together. All this testing in a second, 1 second of time. Now that's the complexity. Now we need to have a design, testability, manufacturing all integrated together. So there needs to be a high level planning to start with in the product development, so that essentially you can test this whole thing in 1 second. That's the test part of the challenge. Now, the problems that we're dealing with, even say all the semiconductor companies and all the esteemed colleagues who are here from different companies, right? The common problems that we are facing is, today the problems are multidisciplinary. So there is no, I would say there's not much of a bifurcation between a hardware and a software. Take any component, there's going to be a hardware part of it, there's going to be a software part of it, no doubt on that. So it's hard to bifurcate, electrical engineering from a computer science engineering. It's not possible today. There needs to be a software, and the software needs the hardware to run on, right? So it's very interlinked. So the skill set of the students, it's very important to understand that let's not segregate ourselves as electrical engineering. So I'm more the experimental guy or the lab kind of person, and the computer science graduate is happy to sit and code. Yeah. Now, if a computer science engineer is running a code on a computer and he gets an error, okay, he or she will go back to the code, debug the code, find out where the syntax error is, maybe rerun the code, and then finally get it working. Okay, great. Now, as an electrical or a semiconductor engineer, if you design something, if you make an IC or if you fabricate an IC, you get the IC back in your lab and you want to test it, right? That's the real scenario what we are dealing with. Now, imagine when you put it on the PCB or the breadboard, wire it up, power it up, and suddenly nothing is working. Circuit is not working. What do we do now? So the ability to understand how to debug the hardware, right? We got something in circuit, we designed it, we manufactured it, we know it's supposed to work in a certain way. But the reality is that Murphy's law, what we expect to work doesn't work in the lab. So then there needs to be ways which we have to plan in advance to see what if scenarios, under what circumstances will the circuit cannot work. How do I debug my hardware, right? So that the debug part is this understanding how we debug these circuits is again an art. It starts from the design, it starts from planning, architecture, incorporating the test, incorporating the ways where you can access these ICs. So all of these are some of the challenges. Second thing is about reliability, one of the aspects about hardware design is also about reliability. And these are topics that are the reason why I'm focusing on this is because some of these topics are not really taught in depth in let's say a BTech or maybe even an MTech curriculum, and they're very, very important for industry. Imagine that we want to design an amplifier that goes inside a smartphone. Okay, and this how often do we change our smartphones? 2 years, 3 years, and maybe somebody like me 4, 5, 6, 7 years. So if a circuit is going in a smartphone, we want the circuit to be functional and operating at its performance for a certain duration of time. Imagine the same circuit now is going into a car. You want to design the same amplifier and put it inside a car. How often do we change our cars? Right? Not too often, right? Not like we don't change our cars like smartphone, especially most people, right? Maybe 10 years, 15 years, that's the time where the car is supposed to work. The same amplifier, imagine it's going to a satellite, Chandrayaan 3 or some other piece of equipment or an application where the lifetime of this is going to be much, much longer, or a satellite. So the same piece of design, same electronics, same principles, when you put it in a different application, has different lifetime reliability requirements, right? So now you would have had your students telling you, for example, when you take a Viva, they will tell you that, madam, the circuit was working yesterday. I don't know what happened. It's not working today, right? It's a very common scenario. I'm sure all of you have experienced. I gave this reason excuse also to my professor, and I'm sure you will hear this almost every day on a daily basis, right? So there's probably a good reason why it's not working. Could be an easy strike. No, so the awareness about electrostatic discharge is very important. Now, once you have a piece of hardware, right, when you're manufacturing something, how do you know that a circuit that is designed today will actually work for 10 years? I mean, there's no time machine anywhere, right? No. How do you predict? So for this, the classic example is treadmill test. I'm sure if you go to a cardiologist, how many of you are aware of a treadmill test, right? Basic cardiac test. What do they do in a treadmill test? They put you on a treadmill. You are asked to run. You have all the electrodes connected all over your body, and then you run. They slowly start increasing the pace of the speed of the treadmill. So, running, your heart rate is now increasing beyond your normal. It's going up, going up, going up to the point where you say, please stop, I'm done. Then they reduce the speed, get back to the normal routine area. So what are they doing in this? They are stressing your heart. Okay, they're stressing your heart to the point where your heart is able to respond to it, and they are seeing a feedback on how your heart comes back from this stressed environment back to normalcy. So what is your recovery? What is the recovery time? What is the recovery duration? How fast it's recovering for a heart? And looking at the response, the doctor is able to say, okay, good, your heart is looking good, or maybe you have a problem, so you need to do this to cut down on these things. Get back, do some walking, do some exercise, come back in a month or 2 months time, right? So he's trying to look at the response of your body to a stress. Please underline the word stress, and then making predictions on how long your heart is going to survive, or how long your heart is going to be working. Apply the same logic to your semiconductor circuits, right? The way you can predict how the circuit works is now stress your circuit. And how do you stress your circuits? You only have power supplies, right? Let's say a circuit is supposed to operate at 3.3 volt or a 5 volt or a 1.8 volt, right? And let's assume your circuit is operating in a mobile phone. Typically for this consumer goods, the temperature where this circuit is working is usually between maybe minus 20 degrees to 50, 60, 70 degrees, right? That's the typical consumer grade temperature. So if you now take this circuit and then maybe stress this more across temperature, take this circuit, make sure that it is operational, and then take it to 125 degrees centigrade, even though it's not needed in your application. Okay, 125 degrees centigrade, 150 degrees centigrade, stress it. Instead of a supply voltage of 1.8, stress it to 2.4 volt, and then so on. See how the circuit behaves under this stress, the electrical stress, the temperature stress, sometimes even mechanical stress, and so on. Just the soldering, those of you are aware, just soldering itself is a stress. When you take it to 300 degrees centigrade, you cool it back, that's a stress already to your circuit. Now, once you measure back the results of your IC or whatever you've manufactured, and look at where you started with something, some parameters, some numbers, some way your circuit is behaving, and then you look at the drift, which means how much the circuit has changed after this stress. Now use this to build your model. There are smart people who have come up with a model. Arrhenius equation is part of the basic. If you do a basic reliability course, they talk about Arrhenius equation, where they say if a circuit works for 1000 hours in 120 degrees centigrade, then the circuit will operate well for maybe 10 lakh hours at 85 degrees centigrade. So you're kind of making a correlation. You use your reliability, design for reliability concepts to make a correlation to estimate how long you can make the circuit work. This is it. So this is basically the concept of design for reliability. So in the end, the goal is always, to make sure that not only design something, but also ensure that the design is meeting the requirements and taking care of the lifetime requirements of the particular application. Now, coming back to the question or theme of the day on what the students need to do and so on. So, few thoughts on this. I think to start with, in my humble opinion, a BTech in an ECE is probably just scratching the top of the requirements of a semicon industry product development. Because it's very diverse. The BTech essentially is, if you look at the history, right, we start teaching C programming on semester 1 or semester 2. You agree? Right? Maybe first semester of the engineering, you start teaching C. So this means the curriculums, essentially, if you look at the sequence, the curriculums are tuned to generate software engineers. Even though we call it as an ECE, in reality, we teach them C code. And at what semester are we teaching them Verilog or VHDL or getting them used to a cadence scenario? Maybe second year, right? If they are lucky, second year. So already first semester, people know how to code C language. They have their laptops. They don't need any great infrastructure to build an app. So naturally, the tendency of a student is once they gain a skill set of building an app, right? They already see something working. It's already a great feeling. You design something, you can make something work with your skill set that you've already learned. So the curriculum, what we have, essentially is more fine-tuned towards generating software engineering, which was a requirement. I mean, this was a requirement, I would say maybe 10, 20 years back. This was our requirement, to have people who can code. But I think, as we move towards generating more and more, we want to create a talent pool for semiconductors. We have to start introducing students to semiconductors well in advance. We have to start introducing students to experimental learning, sit in the lab, get some things done, make things work, and see how things work, see how things don't work. Ensure that, if something is failing, understand, debug why something is failing, why something is not working. So all these real experiences, experimental learning in electrical engineering is a must to really build a semicon talent pool. Point number 2 is that, like Venkat sir has said before, it's a tough discipline. Let's accept it. Electrical engineering, electronics, semiconductor engineering is, I would say, a culmination of many of them. It's not so you need software, you need hardware, you need understanding of physics, you need understanding of material, you need understanding of optics. Incidentally, I come from a company where you might not know the name of the company, but you use all our parts. So all the mobile phones that you're using, as soon as you get a phone call and you keep your phone close to the ear, the display shuts off, right? Why does it shut off? What's the purpose? Why does it shut off when you keep the phone close to the ear? It's not required. Eyes and ears are perpendicular. You don't need to see your phone as soon as you keep your phone close to the ear. And this job is done by a simple proximity sensor. So it's detecting the distance between the sensor interface and the body or the screen or whatever is the object that's outside the sensor. Based on intensity of the received signal, the reflected signal, you decide whether, okay, you are far apart or is there something close. When something is close, the assumption is that you don't need to see the screen, shut off the screen. Okay, this is to save the power. And just this application of optical sensors, where your signal is a light that's coming out of a tiny package, which hits your ear, and then you sense back the reflected thing. Imagine the same scenario whether you have, let's say we are fair skinned, we have white hair, moisturizing lotion. So the reflected intensity is now changing based on the person who is using it. White reflects more, black reflects less, right? Moisturizing lotions have a different impact. So the use case application creates more and more scenarios and more challenges. So this means it is very important not only to say, okay, I know this, but it's also very important to understand what I can learn. So the concept of self-learning is very, very important for students. The information is all available everywhere. There's tons of information available in the internet. Anybody can go and learn, but there needs to be a willingness to learn. Not everything can be taught in as part of a course semesters. The courses are only to really inspire students, to really work hard and then do it. So the self-learning is something that I would strongly encourage, you as faculty members, please motivate the students to, go back, learn the subjects, try to read, technical papers, journals, try to see what are the upcoming applications. There are several, state-of-the-art information that are available. Read through that, and then hopefully, this will inspire them to take up semiconductor as a career option. And I would like to conclude my short talk with a statement saying, semiconductor engineers, good semiconductor engineers are really worth their weight in gold. Believe me. So there is brilliant career options available, very extremely lucrative financial packages that might not have, we think also the the Amazons or the Googles that have these lucrative careers. But good semiconductor professionals also have great careers, and then very fulfilling, satisfying careers. And a note from being in industry, I also teach in university, so I'm a visiting professor at IIT Hyderabad. So it's also important that as experienced industry professionals, we spend our time teaching as well. So experts from industry have to teach, and this is where we can start bridging the gap.